Here's section 9.5, and one piece of paper. It has to be a pretty exciting, happy thing for you, I guess. When there's only one piece of paper, that's always a good sign. And we have one test to do today, and it's our alternating series test. With that test, that's a pretty easy thing that we'll look at and determine, I guess, whether our series converges or diverges. With this, though, we also have our alternating series remainder, and we have a couple questions that deal with that. And then we also have absolute and conditional convergence and the difference between them, and determining then if a series will absolutely converge or conditionally converge. So it is one piece of paper, but there's a lot of different things that we can do with our alternating series. So if we just look at our alternating series test, we're going to let a sub n be greater than 0. And so with an alternating series, it's obviously alternating in these two situations, because you can either have -1 to the power of n or -1 to the power of n plus 1. But both of those situations are going to make it, obviously it's alternating. And then we will need to identify what is this a sub n. Well, these series will converge if the following two conditions are met. And they're very easy conditions. The first one, the limit as n is approaching infinity, whoa, I put 0, as n is approaching infinity of a sub n, this has to be equal to 0. Well, that's pretty basic, and we actually know that from back in section 2, we talked about this, that if your limit of like the sequence portion of this doesn't equal 0, well then it's going to diverge by your nth term test. So that's the first condition that has to be met. And the second condition is that your terms have to be decreasing. So a sub n plus 1, meaning our next term, has to be less than or equal to a sub n. And this would be for all n. So really, the alternating series test is really awesome. It's pretty darn easy, about as easy as it can get. If we look at two examples here for our alternating series, this first one, number 14, obviously it's alternating because we have the -1 to the power of n. And then we have our natural log n plus 1. So yes, it's definitely alternating. As soon as you see this, we like to use our alternating series test, again, because it's super easy. You have to show two things, though. The first situation is your limit n is approaching infinity and of a sub n. So don't include the alternating portion, so it's basically the absolute value of this. And it'd be 1 divided by natural log n plus 1. And this has to equal 0. Well, if we look at this, infinity plus 1 is infinity. Natural log of infinity, although it increases incredibly slowly, is infinity. Maybe I should erase this for now. Using direct substitution, we know that we create 1 divided by infinity, which is equal to 0. Great, our first condition is met. Then our second condition are the terms decreasing. Well, if I look at it, and if I have natural log, and in place of n I put in n plus 1, that's going to become n plus 1 will give me n plus 2. Is that less than 1 divided by natural log n plus 1? Well, again, it increases slowly, but this term here is going to be bigger than this term, so this denominator. So when you put it into a fraction, yeah, that definitely works. You could graph these two. These two graphs would be so close together that it would be a little bit difficult to tell, but you could also look at the table values on your calculator, and these values are definitely going to be smaller than these values. Therefore, because both conditions are met, this series converges, and we can write after it, it is our alternating series. So, pretty darn nice. It can be disguised a little bit here, and in this situation it doesn't look alternating like number 14 was obvious. Okay, that's alternating because we had the -1 to the power of n. And so we'd have to rewrite this series to start, and usually there's a little hint like, hey, rewrite this series or rewrite it using alternating series to tell you just a little thing on what to get started with. And it's this cosine n pi is what we're going to be replacing. So if we look at it, well, cosine in place of n, if we put in a 1, cosine pi is equal to -1. So our first term is negative. If I plug in a 2, cosine 2 pi is equal to a positive 1. If I plug in a 3, cosine 3 pi is negative 1. So we can replace this portion with an alternating series, and that would be negative 1. It'd be to the power of n because we do want that first term to be negative. So if I plug in a 1, yep, my first term is negative. Great. My second term, if I plug in a 2, it's going to be positive. So that cosine n pi, I can replace it with negative 1 to the power of n. And now the 1 over n, I'll keep it here. Now it obviously looks alternating. Alright, let's test using our alternating series test. We have two conditions. The first condition, the limit as n approaches infinity. Remember, we take the absolute value. We're not concerned about the alternating portion. So that leaves us with 1 divided by n. When we use direct substitution, we get 1 divided by infinity, which is equal to 0. First condition is met. The second condition is 1 divided by n plus 1, less than 1 divided by n. Absolutely, because that basically that term, that's going to get bigger, which if I have a bigger denominator, it's going to be smaller, I guess, than this next one. So second condition is met, therefore converges alternating series. And looking at this, alternating series converge pretty darn easily then. It doesn't take too much. Alright, we do have an alternating series remainder, and this is theorem 9.15. If a convergent alternating series satisfies the condition a sub n plus 1 is less than or equal to a sub n, so again, terms are decreasing, then the absolute value of the remainder involved in approximating the sum s by s sub n, so that's partial sums, is less than or equal to the first neglected term. So that first neglected term we will be using in this situation. To write this out, basically we want the absolute value of our sum minus the partial sum. This is going to equal our remainder, which has to be less than or equal to, because it's that first neglected term, a sub n plus 1. And as we go through a couple examples, I think you'll catch on of what this actually means, what we're looking for. And there's really two types of problems that go with this. So right now I totally understand that this is maybe a little bit confusing. Just follow along the examples, and then we'll look back at what the alternating series remainder says, and hopefully that will help clarify things. So there are two types of questions that go with your alternating series remainder. Number 36 here, and then on the back you have number 38. And these are two different problems, but they're good. They're obviously used in using the alternating series remainder. So we want to approximate the sum of our series by using our first 6 terms. So if we use our first six terms, we want our partial sum of our first 6 terms. When we plug in a 1 for alternating, our first term will be positive, and then from there we can just say, okay, well then it's obviously alternating negative positive. And that would give me 1/2 when I plug in a 1. Plug in a 2, I know it's going to be negative, and I would get 2 divided by 4, which is 1/2. My third term, when I plug in a 3, I know it's going to be positive. I have 3 divided by 2 to the third is 8, so 3/8. My fourth term is negative. I have 4 divided by 2 to the fourth, so 16. That would give me 1/4. Plug in a 5, and I know that one's positive now. I'd have 5 divided by 32. The last one is negative. I'd have 6 divided by 64. And that could be simplified a little bit. So our partial sum, when we have 6 terms, is equal to, it's equal to 0.1875. But what this question is asking, and what we want here, We want to approximate the sum by using our first 6 terms, but going back to our alternating series remainder, it says we have to take into account our first neglected term. Well, our first neglected term would be that 7th term. And if we look at our 7th term, plug in your 7, you get 0.0547. So that's our first neglected term. Basically what this means is that the sum lies between, here we have the 0.1875. I have to add and subtract my first neglected term from this value. So when I add it to this, well, I'm going to subtract it first so that I can write it on the left side here. And I know technically after this we should add, but remember the term after that you would be subtracting. So you're going to add a little bit, you're going to subtract a little bit less, you're going to add a little bit less than that, and you just keep alternating back and forth. So I'm actually going to start off with subtracting, and I'm going to say that it's between 0.1328. And remember, I got that because I subtracted it from my partial sum of the 6 terms. That's less than or equal to the actual sum. And then if I add it to this, I have 0.2422. So again, I added my first neglected term. I added and subtracted it from my partial sum of the first 6 terms. And it's because that remainder theorem tells us we have to take into account that first neglected term. So in this situation, it says we are approximating the sum of our series using 6 terms. Well, you're using 6 terms plus the first neglected term. Your answer should be an interval. So I have 6 terms, my first neglected term. My sum is going to be somewhere in that interval. So a little bit weird. I don't know. I think the questions aren't asked the greatest all the time, but that's the type of answer that they're looking for. In this type of a problem, you're looking for, your answer should be an interval. Alright, the next type of question that we have that deals with this alternating series remainder, number 38, and it tells you to use this theorem 9.15 to determine the number of terms required to approximate this sum of our convergent series with an error of less than, they'll give you a margin, so we want here less than 1/1000th. And looking at it, we have to remember we have to keep in mind that first neglected term. Alright, so what I do usually to approach this type of problem, and this is pretty darn ugly looking, what I also think is kind of funny is that they actually tell us what this thing is equal to, which is interesting. But going back to our alternating series remainder, it tells us that we want the absolute value of our remainder. Therefore, we're not going to worry about the alternating portion of it. So we want the absolute value when dealing with the remainder, which means the absolute value of our remainder is less than or equal to our first neglected term. And we have to keep in mind, again, we have to use that first neglected term. So what I usually do is just look at this portion. So I have 1 divided by, again, it's absolute value. I want my first neglected term, so this means I need 2 to the power of n plus 1 times n plus 1 factorial. That has to be less than or equal to 0.001. So as long as finding how many terms, if this term is less than this amount, it's not going to affect the value of it. It's not going to affect my sum. But you have to keep in mind it's your first neglected term. So instead of just copying down the exact sequence that we have in here with the 1 divided by 2 to the power of n times n factorial, it has to be the n plus 1 wherever you have an n. And basically from here it's just trying values. I guess you could try to solve for n if you want to, but you really don't have to. So right on here, let's try some values. Let's just say, well, let's let n equal 3. Part of the reason I know this is factorial, and factorial increases incredibly quickly. And we also have exponential, which increases incredibly quickly as well. So we have 1 divided by, this would give us 2 to the 4th times 4 factorial. And if you have your calculators out to try that, usually you want to start fairly low, and if you're way off, you know, then you're going to have to obviously adjust a little bit. But I got, if n is equal to 3, I got my value for this to equal, even if you want to put x equal, it doesn't really matter. But I got 0.0026. Well, is that less than or equal to 0.001? Obviously no. That didn't work. I'm not far off, so I'm going to try, well, what if n is equal to 4? If this was way off, you might want to jump up by a significant amount. And again, factorial increases really quickly, so that also helps, but we just have to find one that works here. So now I have 1 divided by, if n is equal to 4, I have 2 to the 5th times 5 factorial. Well, when I plug that in, I ended up getting 0.0002 blah blah blah. And is that less than or equal to 0.001? Yes, that works. That the first one didn't. This works. This is good. So that's if n is equal to 4. The question says how many terms do we need? Well, that's when n was equal to 4, so when we plugged in a 4, it was good. That term worked. I started at 0 in this situation. So because you're starting at 0, you have terms 0, 1, 2, 3, and 4, meaning there were 5 terms necessary in order for this approximation to be within 1/1000th of what the actual answer is. If this would have started at 1 instead of at 0 of the series, well, then I would only have 4 terms. And it still, even if I started at 1, that's fine. The problem here doesn't change. The problem here doesn't change. This inequality isn't going to change. It's just at starting point. So make sure you check your starting point when you do this. And the kind of weird questions with that remainder theorem, I don't know, like I said, I don't love how they state the question for the first one that we did, number 36, but it is an interval answer that you're looking for. And this one, just keep in mind that you're looking for that first neglected term, which is pretty basic then. So you just take your sequence, your first neglected term, wherever you have an n, you make it n plus 1. And that value just has to be less than whatever they give you, whether it's 1/1000th or 1/10,000th or 1/100th. It's kind of however the problem is set up. Alright, and the last thing in this section is absolute convergence and conditional convergence. What we're looking for here, and there's always a confusion of what these things actually mean. Absolute convergence basically means that would this converge even if it weren't an alternating series? So does this convert? Absolutely, no matter what, whether it's alternating or whether it's not alternating, does it converge? So basically, if our series, in our series we have the summation, and it's the absolute value of a sub n. So absolute value in this, we don't have to worry about the alternating portion of it. If this thing converges, then the series a sub n also converges. So absolutely convergent basically means, and we can write this underneath, does, how can we write this so it makes sense? So absolute convergence, does the series converge whether it's absolute value or not? Or I don't mean absolute value, I'm sorry. Does the series converge whether it is alternating series or not? So if it converges, if I take the absolute value of it, that's why I screwed up. So the absolute value of it will ignore the alternating portion. If that converges, well, whether it's alternating or whether it's not alternating, it will converge. It is absolutely convergent no matter what. For conditional convergent, What that basically means is if I look at my series and if I take the absolute value of it, if that diverges, well then I can look and say, but the series, if I make it an alternating series, then it can converge. So conditional convergence, we'll write in here absolute value of series diverges. But the alternating series converges. So that's conditional convergence. The absolute value of their series diverges. And why it's called conditional then is basically meaning, but under the condition that it's alternating, then it can converge. Because if it's alternating converges a lot more than your basic series. It doesn't take much to prove it. Alright, so hopefully if we do these two examples, this makes sense. Really look at this. This is a problem usually on tests and quizzes, is what's the difference between absolute convergence and conditional convergence. So for number 50, what you always want to test first is the absolute value of it. So we're going to take this and say, alright, basically, does our series, we have from 1 to infinity, if I look at the absolute value, well I have 1 divided by n times the square root of n. Does this thing converge? Is basically our question. Well, yeah, this is really nice because this is just basically our power series. And we can say n is equal to 1. From n equals 1 to infinity, I have 1 divided by n to the 3/2. My power is equal to 3/2. That's greater than 1. Super easy. Therefore, this converges using our p series. And because the absolute value, I looked at this, I don't have to worry about alternating, the absolute value of it converges, this thing absolutely converges. So therefore, if this one converges by the p series, this one absolutely converges. And absolutely converges means it converges whether I have the absolute value of it. If I have alternating, it is going to converge no matter what condition it's in. Alternating or the absolute value of it, it will converge. Well, if we look at number 58, okay, here's our situation. We want to look, well, does our series from 0 to infinity, I want the absolute value of it. So I have 1 divided by the square root of n plus 4. Does this thing converge? Well, this one's going to take a little bit more work in order to test this. If we think about what tests we want to use, we could possibly try our direct comparison, which means if I have 1 divided by the square root of n plus 4, is that less than, that is less than, sorry, 1 divided by the square root of n. But remember, in this situation I'm comparing it to this one. Here's my power is 1/2. Well, if my larger one diverges, does that mean the smaller numbers are going to diverge? No. So we can't use direct comparison. Direct comparison doesn't work. Alright, we have to take a different test. And you could use limit comparison with this one. That might be better. So if I try limit comparison, you also could use your integral test, and that would be fine. You would have to have a u value, but that's not a big deal. So limit comparison, we're going to say b sub n is equal to 1 divided by the square root of n. Limit n is approaching infinity, and for our limit comparison test, we need to have a sub n, which is our original, divided by b sub n. So a sub n, 1 divided by the square root of n plus 4, 1 over square root of n, which I know you probably just started and wrote this out as square root of n divided by square root of n plus 4. As n approaches infinity, well, let's divide both the numerator and denominator by the square root of n. Now we have the limit n is approaching infinity. We have 1 divided by the square root of 1 plus 4 divided by n. That's going to equal 0. Therefore, this is equal to 1. 1 is a positive finite number. Therefore, limit comparison, I can go back to this situation. That's what I'm comparing it to. The summation of 1 divided by n to the 1/2. My power is equal to 1/2. Therefore, I know that this is going to diverge. So this diverges using P series and limit comparison. Alright, well, the absolute value of it diverged. Where in the last one, the absolute value of it converged. So great, this converges absolutely no matter what. If the absolute value diverges, then we have to check, well, how about if will it converge under the condition that it's an alternating series? So that's why this is called conditionally convergent. The absolute value diverges. It is not absolutely convergent no matter what. Let's check the condition. If we made it an alternating series, then would it converge? So if we look at this portion of it, okay, alternating series, now the conditional part of this is you're just using your alternating series test. So here's your conditional portion. And it just goes back to your alternating series test, which we just learned there's 2 conditions that have to be met. First of all, the limit n is approaching infinity. If I take the absolute value, 1 divided by the square root of n plus 4. This is equal to 1 divided by infinity using direct substitution, which is equal to 0. Yes, that condition is met. Is the second condition met, meaning my terms are decreasing? We'll make this n plus 1 plus 4. So is 1 divided by the square root of n plus 5 less than 1 divided by the square root of n plus 4? Yes, that condition is met. So absolute value of it is divergent. Didn't work. But if I make this an alternating series, then it would converge. So here we could say, you know, obviously this converges. Alternating series. Our final answer here is, therefore, this is conditionally convergent. And like I said before, alternating is so easy to converge. So we looked, under the condition that it's an alternating series, it will converge. If you don't have that condition, it would not converge. So it's this one is conditionally convergent. So always check, you know, when the directions back here say, I didn't put any directions, but test, does this absolutely converge or does it conditionally converge? Always test the absolute value first. If the absolute value of your series converges, it's absolutely convergent. If the absolute value diverges, well then let's test, how about if we make the condition that it's an alternating series? It's super easy to test that. You have the 2 conditions to follow. And if it then will converge, great, it will converge conditionally under the condition that it's an alternating series. So kind of 3 things to take out from this section. Number 1, your alternating series test, which you have to show the 2 things for every time. Number 2, that alternating series remainder, it's a little bit goofy. Make sure you remember the first neglected term. You only have 2 types of problems that go with it. So you have 36 and 38 in your examples here. And then this absolute versus conditional convergence. And this last thing, it tends to be an issue on quizzes and tests. So make sure you know what it means to be absolutely convergent versus conditionally convergent. And I probably should have showed that before I started my spiel there. Page 636, here are the numbers that you have. You have plenty of class time to work today. Make sure that you check your answers, that you work with somebody, that you get to the conditional and the absolute convergence, and do the best that you can. Have a fantastic day.